This is the intro video for AP Calculus, BC, section 7.2. We're going to be looking at volume by disks and washers. The disk method is a way to find the volume of what we call a solid of revolution, and that is a three-dimensional shape formed when the graph of a function or a region is revolved around an axis. So we have some good there we go. There's some. I have another good video of this. I know the AB video. I put in some good visualizations using like Wolfram Alpha. Feel free to check that out if you're having a hard time visualizing this. I'm going to draw a picture here for you. So let's say that we have some region. Let's say that that region is here in the first quadrant. Something really simple. Parabolic looking thing, maybe exponential, something like that. So that region right there is going to be the region that we care about. And what we're talking about here is, what if we took that region and we revolved it around the x-axis? So in other words, it kind of came out of the page at us and then back down into the page, something like that. That would form, kind of like a funnel-like shape, I guess, it could look something like this if we, kind of moved it around a little bit. The x-axis in this case would be coming straight out at us, and then going back into the region, something like that. So what we're basically talking about is finding these three-dimensional solids, figuring out what their volume is. We can figure out the surface area, things like that. But we're just going to be focusing on volume here in this section. So to help us with this disk method, we're going to visualize a disk using a representative rectangle. So let's take a look at that here next. So using that same region, or roughly that same region, something like that. I'm going to just take a little chunk of this, our little representative rectangle, and we're going to think about what that would look like if I revolved that around the x-axis. So if I took that representative rectangle, we're going to kind of three-dimensionalize this a little bit. There's the representative rectangle on the other side. Go something like this. Let's try that one again. And you end up with this, literally a disc. It looks like a DVD or a Blu-ray or something. You could look at another representative rectangle here and make another smaller disc. But these are simply going to start accumulating. I mean, the biggest one would be back here. Looks something like that. And then go back up into the back of the page there. So we're going to be taking these discs, and I'm going to just draw one of them out here, and using those to help us find volume. So there's the disc. The axis of rotation would be coming right out of the middle. So I'm just taking one of these and just kind of drawing it over here to visualize it a little bit. So we're going to be finding volume. So let's think about what this volume would be. If you think about a disc, it's really just a cylinder. And the volume of a cylinder is pi r squared times h. And on this picture right here, this little flat part here would be the h, would be the height. The cylinder's been tipped on its side. And then, of course, the radius is what goes from the center of the figure out to the outer edge. So that's the radius right there. And so we end up with this pi r squared h concept, but we're talking about disks that are approaching a thickness or a width of 0. So instead of using an h right there, what we would use is a dx, or potentially a dy. In this case, it would be a dx, but in other cases, maybe it would be a dy. We're going to be accumulating those super skinny disks, and there's going to be infinitely many of them, and that'll give us the perfect exact volume of the figure. So one important note here for the disk method, and really for the washer method, which we'll look at later, the representative rectangle has got to be perpendicular to the axis of rotation. Okay, so based on the formula we looked at up here for the volume of a disk, let's look at the formula using the disk method. So if you're going to be using a horizontal axis of revolution, everything's going to be in terms of x. If you're going to be using a vertical, everything is going to be in terms of y. Let's take a careful look at what's going on here. Hopefully you can see this. Essentially, it's just pi r squared and pi r squared. They've pulled the pi out of the integral because it is a constant multiple. Of course, that's okay. But it really is simply just pi r squared times dx, or pi r squared times dy. In order to get this, we accumulate along the region that we're interested in, and we'll get the volume. So in both cases, the r stands for radius, and I'm going to actually switch screens here real quick. There we go. So the r stands for the radius. Another way to think about it is it's the distance from the axis of rotation to the outer edge. And of course, I'm just describing a radius there, but sometimes that wording is a little more helpful in describing what's going on. Okay, and of course, dx and dy are both thicknesses of the representative disk. One of them is in terms of x, the other one is in terms of y, and of course that all just depends on what the axis of rotation happens to be. Okay, let's do an example. Okay, number 1 says find the volume of the solid formed by revolving the region bounded by the graph of f of x equals cosine x and the x-axis on the interval 0 to pi over 2. We're going to be revolving around the y-axis. So we're going to sketch a graph of this first. Here's what it could look like. Here is the y and the x-axes, and then cosine of x, y equals cosine of x, does this, and it actually does hit the x-axis right there at pi over 2. So we're going to be taking that region bounded by the graph there on the interval 0 to pi over 2. We're describing this region right here, and we're going to be revolving that around the y-axis. So I usually put just a little revolution symbol there, just signifying what my axis of revolution is. And I'm going to draw my representative rectangle next. The representative rectangle has to be perpendicular to that axis of rotation. So I'm going to draw in a representative rectangle that looks like this. It's not tall and skinny, it's actually kind of short and wide. And so this representative rectangle would have a thickness of dy. And the reason why I draw that representative rectangle in first is because I want to establish what the thickness of the representative rectangle is, because that is going to tell me what the rest of my integrand and the whole integral, everything is going to be in terms of. So it's going to be in terms of y for this one. Okay, so I'm going to be using the disk method here. So volume equals pi times the integral. Let's figure out our limits of integration here. Limits of integration, since we have a horizontal representative rectangle, we're going to be accumulating from the bottom of the region to the top. So we're going to go from 0 to where? Well, up here. Hopefully we remember that that high point on cosine of x is 1. So we'd stop accumulating at 1. So pi times the integral from 0 to 1. And then my radius, my distance from my axis of rotation to the outer edge of the figure, would be represented by this, from this blue dot here to this blue dot here. And of course, that distance is going to vary. You know, up there it's that length, down here it's a little bit longer, at the top it's very short. So it's going to be a variable. And here's where I'm going to build this up just a little bit, and we won't have to do this every time, but I'm going to just say that as we know it, from the y-axis out to the right, we know that is an x distance. And so what I would do here is I would say that my radius is x and my thickness is dy. So pi r squared dy right there. So this would be a step that you don't always have to put in. In fact, I would say, as you get better at this and you move forward, you'd rarely do this. Of course, we have a little bit of an issue here because everything has to be in terms of the same variable. The dy is not going to change. And so that means the x is the thing that has to change. And so what I'm going to do here is I'm going to try to figure out what can I replace that x with that is only in terms of y. And the key would be then to go back and look at this and realize that y is related to x using cosine. So we'd say y equals cosine of x. How do I get the x by itself? Well, I would do inverse cosine of y of both sides. There is equal to x. So I could replace the x with inverse cosine of y. Okay, so this did say find the volume, and say at this point we would use a calculator to evaluate this. So let's do that and see what the answer is. All right, so I got 3.586 if you round to the 3 decimals. Easy things to forget when you're putting it in the calculator: the pi, the squared. So be careful that you do that. Just watch out for that and you should be good. We will work another example when I see you next time in class.